Hello everyone, welcome back to my Journey Education YouTube channel. Today we are taking one of the most classic and elegant problems in all of computer science. It is the Tower of Hanoi. If you ever taken a data structures and algorithms course, you have definitely seen this. It looks like a simple child game, but hidden within it is a powerful concept that unlocks a whole world of problem-solving recursion. By the end of this video, you won't just know how to solve the puzzle. You will understand the beautiful recursive logics that makes it work every single time. So, whether you are a student preparing for an exam or curious mind, stick around. Let's get started. What you learned today? What exactly will we cover? You are going to do a complete breakdown of this puzzle. You will start with the problem definition and its strict rules. Then we will unveil the recursive solution that I like to call the magic algorithm. After that, we will make it all concrete with a step-by-step example using 3 disks. And finally, we will analyze it to understand just how powerful and frankly. To be more specific, our agenda is problem definition. What is the puzzle anyway? The recursive solution, the core of the video, step-by-step example, a full walkthrough with 3 disks, analysis and complexity, where we see the exponential growth. Alright, let's jump into part 1, defining the problem. What is the problem? The Tower of Hanoi isn't some new frank coding challenge. It is a mathematical puzzle from the 19th century invented by the French mathematician Edward Lucas in 1883. But computer scientists absolutely love it. Why? Because it is a perfect self-contained example to understand recursion. It is a simple to visualize, but it is solution teaches you a fundamental way of thinking that is crucial for programming. The components. So, what are the components? It's a very simple. We have 3 pegs, typically called the source peg, which is where all the disks start. Second one, the target peg, which is where we need to get them to. Third one, an auxiliary for helper peg, which we will call B. And we have n disks. These are all different sizes and they start on the source peg in a stack, with the largest on the bottom and the smallest on top. The objectives. The goal is straightforward. We need to move the entire stack from the course peg to the target peg. And this is the crucial part. We can't just pick up the whole stack. We have to follow two very strict rules. The rules. Rule number 1. You can only move one disk at a time. So, no cheating. Rule number 2. You can never place a larger disk on top of smaller disk. This is the rule that makes the puzzle challenging and forces you to use the auxiliary pred strategy. So, to recap, move the whole stack from A to C one disk at a time without ever breaking the size order rule. The recursive solution. Now, for the main event, the recursive solution, before we apply it to Hanoi, let's quickly remind ourselves that recursion is. What is recursion? In programming, recursion is just a method of solving a problem where the solution depends on solution to smaller intents of the same problem. I love to think of it like a set of Russian nesting dolls. To open the biggest doll, you have to open the slightly smaller one side inside it, and to open that one you have to open to the even smaller one inside it, and so on until you get to the smallest solid door. Every recursive function has two key parts. First one, a base case. This is the simplest, smallest version of the problem that you can solve directly. It's the solid door that stops the process. Second one, recursive step. This is where the function calls itself but with slightly smaller or simply input. This is the opening the bigger door to find smaller one step. The base case. So, what's the solid door for the Tower of Hanoi? What's the absolute simplest version of the problem? It when you only have one disk. If n equals 1, the solution is trivial. You just pick up that single disk and move it directly from the source peg to the target peg. Done. This is our base case. The recursion stops here. Now the magic happens when we have more than one disk. Let's say we have n equals 3 disks. How do we solve it? The recursive mindset is this. I don't know how to move 3 disks yet. But what if I could magically move 2 disks? Then I could solve it. And that's exactly what we do. We already have function that can move 2 disks. So to move 3 disks from A to C. First you use our magical function to move the top 2 disks from A to B. A is source and B is auxiliary. We use C as the helper for this step. Second, now the largest disk is exposed at the bottom of A. We move that one disk directly from A to C. This is easy, and it's like our base case from the biggest disk. Finally, we use our magical function again, move that stack of two disks from B auxiliary over to C target, using A as the helper now. Did you see that what we did? We broke the n equals 3 problem into n equals 2 problems and one simple move. The algorithm. Let's formalize this intro into a general algorithm to move n disks from source to target using accelerate. Step 1. Move the top n-1 disk from the source peg to the auxiliary peg. Step 2. Move the one large nth disk from the source peg to the target peg. Step 3. Move the n-1 disk from the auxiliary peg to the target peg. The algorithm is beautiful, self-similar. It works for 64 disks, 10 disks, or 3 disks. It's recursion in its purest form. Part 3. Step by step example. I know that can sound a bit abstract, so let's make concrete. Let's solve puzzle for 3 disks, following our algorithm exactly. Our initial state 3 disks on peg A. Our goal is to get them all to peg C with peg B as our helper. We start with all disks on A. Step 1 of the algorithm is to move the top n-1 disk from A to B. But how do we move 2 disks? We use the same algorithm recursively. So, to move 2 disks from A to B using C as helper. Move 1. Move the smaller disk from A to C. Move 2. Move the medium disk from A to B. Move 3. Move the smaller disk from C to B. On the top of the medium one. And there we have it. Step 1 is complete. The top 2 disks are now safely on peg B. The largest disk is alone on peg A. Step 2 is now trivial. Move 4. Move the large disk from A to C. This is a huge moment. The largest disk is now on the target peg, where it will stay forward. It's out of the way. Now, for step 3, move the n-1 disk from B to C. Again, We use our recursive algorithms to do this. Move 2 disks from B to C. Move 5. Move the smaller disk from B to A. Move 6. Move the medium disk from B to C on top of the large one. Move 7. Finally, move the smaller disk from A to C on top of stack. And we are done. In exactly 7 moves, we have successfully moved the entire stack from peg A to peg C. Following all the rules, this is the most optimal solution possible. You literally cannot solve it in fewer moves. Analysis and complexity. So we solve it, but how efficient is this? Let's talk numbers. The numbers of moves required follows a very specific formula. 2 to the power of n minus 1. Let's see some examples. For 3 disks, 2 to the power of 3 minus 1, 8. Its answer 8 minus 1, 7 moves, which matches what we just did. For 4 disks, 2 to the power of 4 minus 1. It's 16 minus 1. It's 15 moves. For 5th disk, 2 to the power of 5. It's 32 minus 1. It's 31 moves. You can see the number of moves in growing you very quickly. Why that formula? Where does this 2 to the power of n minus 1 come from? It comes from the algorithm itself and is called the recursion relation. Remember our 3 steps? First one, to t multiplication by n minus 1 moves. Step 2, to 1 move. Step 3, to t multiplication by n minus 1 moves. So the total time for n disks is t multiplication by n equal to multiplication by t multiplication n minus 1 plus 1. If you solve this recursion relation, it simplifies directly. T multiplication n equals 2 to the power of n minus 1. This is a classic example in algorithm analysis. The power of exponential growth. Let's appreciate what exponential growth really means. This is where it gets crazy. 3 disks minimally 7 moves in 7 seconds. 10 disks minimally 1023 moves. It's 17 minutes. 32 disks. It minimally 4.3 billion moves. It's 136 years. 64 disks. It minimally 18.4 quantity. It 585 billion years. Look at that, where there's a legend that physicists are working on this puzzle. With 64 golden discs in a temple, and when they finish, the world will end. Now you can see why it would take longer than the current age of the universe. This is why we say the Tower of Hanoi has exponential time complexity, which is considered highly inefficient for large N. Key takeaways. So let's recap our key takeaways from this deep dive. Simple rules, complex solution. The puzzle has only two rules, but they lead to a beautiful complex solution. Recursive solution. The key is to break the problem down. Solve for n-1 disk first. The algorithms move n-1 move 1 move n-1 is all you need to remember. Exponential complexity. The number of moves to the power of n minus 1. This is fantastic demonstration of how some problems became incredible very quickly. Course's concept. This isn't just a puzzle. It's a fundamental tool for understanding recursion, recurse, relations, and algorithmic thinking. And that's the Tower of Hanoi. I hope this video demystified recursion for you. If you have any questions, drop them in the comments below. I read every single one. If you found this helpful, please hit that like button and subscribe for more deep dives into data structures and algorithms. As always, image sources are provided in the final slide. Thanks for watching, and I will see you in the next video. Thank you very much.